Hello everyone, I'm Zhiyuan Lu. Now I'm going to introduce our work improving the performance of NVM crash consistency under Multicore. The first is the background, including NVM crash consistency, ADR, and LAD. The main issue in NVM system is to keep crash consistency, which means that the system is recoverable to consistent state after feature, like power loss. Consider the example to insert a node C to the linked list. First, the next pointer of C points to B. Then change the next pointer of A to C. If crash happens on this step, without support of crash consistency, this list will be broken and in inconsistent state after recovery. For ADR, it's a synchronous DRAM refresh, which is proposed by Intel to safely persist write request in memory controller to NVM in case of power failure. As we can see, the write buffer supported by ADR, here we call ADR buffer, is in persistence domain. Recently, LAD proposes a logless crash consistency scheme if the size of transaction is smaller than ADR buffer. To achieve this, transaction updates accumulate in ADR buffer during execution and are flushed to NVM when transaction ends. Here is the example. It is assumed that ADR buffer size is full, and there are 3 unique updates, W1, W2, W3, in transaction T1. As we can see, updates first accumulate in ADR buffer, then reach transaction end. Right now, suppose there is a crash with the ADR spot, contents in ADR buffer can be flushed to NVM safely. However, LAD falls back to log if ADR buffer overflows during execution. Our motivation is based on the shortcoming of LAD and consider the concurrent transaction execution under Multicore. Based on former assumption, we introduce another transaction, T2, which has 5 unique updates. In the first case, updates from T1 and T2 admitted to ADR buffer concurrently, and when T1 sends T1 W3, ADR buffer overflows. So in this case, we need to log T1 and T2. This causes 8 log writes. Next, we admit T1 and T2 to ADR buffer sequentially. First, T1 updates accumulate in ADR buffer, and then T1 ends. Contents in ADR buffer can be flushed. Then T2 comes. It causes ADR buffer overflow. In this case, we only log T2, which is 5 log writes. As we have seen, with suitable admitting scheme, there is no necessary to log T1. Based on these 2 examples, we found that first, concurrent transactions compete for limited ADR buffer. Second, ADR buffer contention causes many unnecessary logs, such as T1 in the first case. Our experiment shows that there are many unnecessary logs. It can be 59.5% and 28.3% in average. Based on our observation, we propose this virtual ADR cooperated with ReduLog. Virtual ADRs are private SRAM buffers for each core in memory controller. I will use former example to show how our design avoids unnecessary log for concurrent transactions. In the first, updates from different core enter their virtual ADR. T1 ends without virtual ADR overflow. Its updates are sent to ADR. However, T2 exhausts its virtual ADR and has to perform logging without consuming ADR. In this case, we adopt ReduLog because it enables faster commit speed. We compare our design with LAD, and we can see in the first graph, virtual ADR almost eliminates all unnecessary log. For performance, ReduLog improves throughput by 20.1%. Virtual ADR with ReduLog improves throughput up to 78.6% and 36.2% in average. In this work, we observed that there is a significant amount of unnecessary log under Multicore in LAD. So we propose a design which avoids unnecessary log for concurrent running transactions. To do this, virtual ADR is introduced to filter transaction with large write set. To further improve performance, we adopt ReduLog. As we have seen, virtual ADR eliminates most of log operations up to 94.9% compared with LAD, and virtual ADR with ReduLog increases transaction throughput up to 78.6%. This is all work we have done. Thanks for your listening.